Assalamu alaikum guys, how you doing? Today I'm going to talk about a new concept to you, which is called the influence lines. And I'm going to start actually by talking about what we know so far, right? So what we know so far is, or what you have taken up to this point, is we would usually give you a beam like that, okay? We would have a load, P, at some distance A, whether it's maybe 2 meters, 3 meters, it depends, but this load here is constant. So this load doesn't change. And then we would ask you to find the reaction AY and the reaction BY right here, right? And then we would ask you also to find the shear and moment diagram. So you would do that for us, and you will find the moment and shear diagram. But again, this load here is constant, doesn't move. And then we could actually find how the moment diagram would change along this beam according to this load P. So that's why we say A here is fixed, so this doesn't move. And then X is the variable, which means that I can find the moment at any section, right? If I want the moment right here from that moment diagram or shear diagram, I can find it based on the fact that this load is not moving. It's fixed in place, it does not change. Okay, so for that I can find again the axial force if present, but there's no axial force here, but you know where I'm going with this. We can apply this to the frames as well if we would need to. This is being my shear force and this is being again my moment. So for that particular beam I can find anything, right? But again, provided this P here stays constant, stays put, it does not move whatsoever. So that's what we have done so far. So now going to another problem. So let's say that the load is start to move. And we know that we have moving loads. Just to give you some few examples, trains, trucks, on bridges, just to name a few. Okay. So now the question becomes, so as this load is moving, what will happen to my reaction A, for instance, and B? Now here in this case, what is happening that now this section SS here is fixed. Okay, so I want to know what happens at this section S, meaning what is the moment, what is the shear, okay, and if that's part of the frame, maybe what would be the axial force. Now if this load P is changing or moving, okay, so that's what I'm looking for. So let's say at X is equal to 2 meters, tell me what the moment MS is, okay? Then if the load moves to 3 meters, so let me call this MS 2 meters, I'm just making up numbers here, right? Then let's make this, for instance, 2. Then let's say I want this to move to 3 meters. So tell me now, what is the moment at 3 meters, right? And at the same time, also, you will notice that the reaction also will change. So you will have AY at 2 meters, and you will also have AY at 3 meters, which also means you're going to have BY at 2 meters, and you're also going to have BY at 3 meters. So the concept of influence lines is, okay, give me a drawing or a diagram that will show me how the reaction force, shear, moment at a certain location, at a constant location, will change with the load. So that's what I'm after here. So as you can see, as this is moving to 3, I'm having moment at 2 meters, moment at 3 meters. So now I have variable points, and that will enable me to generate a figure or a diagram. That diagram I will call the influence line. Okay, so that again, it's going to show me how my moment and my shear, for instance, or reactions are changing with the change in the position of the load. Okay, which is different from this, right? This is not equal. Here I'm showing you how the moment is changing across the beam as the load is constant, as the code is fixed, it does not move. Okay, so we're going to forget this for a while, all right, and concentrate on this part. Okay, like I said, this part is going to help me in finding maybe maximum moments, maximum shear, maximum reaction as the load is moving. Okay, and that would be my point of interest. So to give you a more general definition, I'm going to say that an influence line for load function, which is going to be the axial force, shear force, and moment at that section. So this section is constant, does not move. The load is moving. The action of the support, okay, which again was my AY and BY. Force in a truss member, we can also use that for trusses, is the curve whose ordinate at any point gives the value of this load function due to a unit load acting at that point. Okay, so let me explain this one more time. So let's say I'm having this beam right here, and I'm having a moving load, whether it's 1 kilonewton, 1 ton, 1 pound, etc. I think it's 1 unit, right? So this load is moving back and forth on that beam. So my interest here, I'm going to concentrate on the moment at C. Okay, I want to know what is the moment at point C. So the influence line, I'm going to use usually an abbreviation. I'm going to call this I dot L dot, which is influence line for the moment at C. Okay, so let's look at this figure, what we're having. And let's start with the obvious one, YC. Okay, so what is telling me? So this value here, YC, is when the load is exactly on top of C. So if I have 1 kilonewton here, okay, for that position, I'm finding my reactions, taking a section at C, and I'm telling you, and I'm calculating the moment. So this value here, or this ordinate, is this value of MC, while the load, the 1 kilonewton, is at point C. Okay? So, okay? So what happens if now my load is at point D? So forget this now. Okay? Forget this and forget that. So now my load, my 1 kilonewton, is at 1 point D. Still, I'm looking at the influence line for the moment at C. So what this is telling me, okay, go find your reaction while this kilonewton is at point D, okay, and then calculate the moment at C. So you will take a section at C due to this load here. So this value here, this ordinate actually, is the value of MC. So this ordinate here at D is the value of the moment at C while the load is at point D. Okay? So moving to YE now, so that again, erase that so there's no confusion. So in this instance, let me put the load at point E right here. So here I'm putting again 1 kilonewton at point E. So here I'm telling you, okay, go find the reaction obviously. So once you find the reaction while the load is here, calculate the moment at C. So I'm still interested at the moment at C. Okay, so this ordinate here, YE, represents the value of the moment at C due to the load being at point E. Okay, so here as you can see, this is showing me, this line like here is showing me how the moment at C is changing while the load is changing. So this graph tells me if my reaction is, if my load is at the reaction here, at the support, then the value of this moment is equal to 0. Okay? If my load is now at point D, then the value of MC is actually YD. If the load now is at C, then this value here, YC, is actually the moment at C. If the load now is at E, this value here is again giving me the value of MC due to the load being here. Now, with the load being at the other support, is also telling me that the value of the moment at point C is equal to C. So that's what this influence line is doing. It is giving me how the section C, obviously you could expand that for the shear at C if you want to, okay? So it's showing me the behavior of the section at C due to the change in the position of the load. Okay, so let me erase that again because I'm gonna summarize what we did so far. So in summary, YD is the moment at C when the unit load is located at D. YC is the moment at C when the unit load is at C. And then YE is the moment C when the unit load is at E. So that's kind of the concept of the influence. So I'm going to start constructing of influence lines for simple beams. I'm going to start with the simplest case, which are the reactions. You will always see me try to find the reaction first and then the rest. And I will explain that later why we do that. Okay? So here in this case, let's say I'm having this load, 1 kilonewton, and it's moving, right? X now is not a constant, it's a variable. I'm going to have AY and BY. So to find AY, I'm going to take the moment at B and let this be my positive direction. So I'm going to have AY times L, right, minus this force, and I want this distance. Obviously, this distance is the total length L minus X, which will equal to 0. So this is giving me AY to be equal to 1 minus X over L. So that's the function for AY. So if I draw this, when X is equal to 0, then AY is equal to 1 kilonewton. When X is equal to L, then Y is equal to 0. And here you can see that this is a straight line. Okay, this is a function of a straight line. Now to find BY, all I have to do is do the summation of FY is equal to 0. Then my BY would be simply A1 minus AY, and it will be 1 minus the 1 minus X over L, and that would be equal to X over L. So if I want to draw the influence line for BY, I will put at X equal to 0, then BY will be equal to 0, which is right here. And when X is equal to L, then this is going to be 1, which is going to be right here. As you've noticed, if you add any ordinate, so if you do a summation, because summation of AY plus BY must be equal to 1, then that summation will be equal to 1 here. So again, here this is being 0, this is 1, which is what we know. So if my reaction is actually at A, then BY is going to be equal to 0. If my force is at B, then AY is going to be equal to 0, and then BY is going to equal to 1. So now let's start with the shear. If I want to draw the influence line for shear at C, okay, then two things are going to happen. I'm going to have a situation where the load 1 kilonewton is before C, and the other situation is going to happen when the 1 kilonewton is after point C. So I'm going to deal with that differently. So I'm going to start with the first situation where I'm assuming, again, oh, by the way, I'm always assuming the positive shear as we did before. I'm using the same sign conventions, clockwise being positive and counterclockwise being negative. So my definition for the shear here is for the positive shear. Here I'm taking X at the location here. So the X values are going to be between 0 and A. So that's going to be my limit. All right. So I need to find VC. So I have two options. Either I use this part right here, okay, but then I have this load 1 kilonewton that I want to deal with, or I could look at this beam right here. It's going to be the same. So that's what I did. So I'm going to ignore the part where the 1 kilonewton is, but again, my X is defined from here to here. That's where is my load is moving. I'm only cheating by taking the other part so that I can have only VC related to BY. And that's what I did. So here, if I take this part, I took the summation, then BY, upward being positive, of course, then BY plus VC is equal to 0, then VC is equal to minus X over L. Again, the limit of X is going to be from 0 to A, okay? So let me refine that X is more than 0 and less than A. Okay, so that's the range. The only thing I did, instead of looking at the left part, I took the right part because it's easier. Okay, now the second part now is my 1 kilonewton now is gonna move after C. Okay, so here I'm gonna employ the same technique instead of looking at this part. But again, the limit here is from 0 to B. Okay, or from A to L if you want. So my X is going to be from this value from A to L. Okay, but where I'm going to look, obviously, I'm going to look at this part here because it is easier. Then summation of Fy is equal to 0, this being upward. Then Ay will be equal to VC. We already found AY to be 1 minus XL, then VC is going to be 1 minus XL. So to draw that, the shear at C, again, since I found that first, and this was represented by minus X over L, so you can see here, as the load is here, I'm only getting negative values for shear, putting X equal to A, so this value here is going to be A over L. Plotting now the other one, where this is now going to be my function 1 minus XL, so this is now going to be my By. As you can see, this is the value B over L, so this is where my negative shear is, which means if the load is moving here, I'm getting a negative shear. If the load starts moving here, it changes from negative to positive shear at C. Okay. Now I'm going to use, before I go to the moment, just know that this value, this slope will end up being of 1 kilo in Newton. Okay. Moment at C, I'm going to do the same technique. I'm going to assume the load is going to move before C and after C. Again, I'm going to take a section. This is what I did. I'm assuming X to be like this, and then this is my 1 kilonewton. Again, I'm not going to look at this part. I'm going to look at the other part. So I can find MC directly. So again, the right part, the limit is still from 0 to A. Okay, so the load is moving here, but I'm just looking at that just to get a function for MC, and that's simply B times By. Then MC is going to be B times X over L. Now, as the load is on the other direction after C, or to the right of C, let's say, then again I'm going to look over here. Same thing, still the limit is from A to L. Now here the moment is just simply going to be A times AY, then MC is going to be A times 1 minus X over L. To plot that, here I'm using Bx over L. Using for X is equal to A, I'm getting AB over L. For the other part, here again I'm using also 1 minus A over L, so that will be B over L, so I'm getting the same value of AB over L. Here this positive value has really nothing to do with whether being tension or compression. This is just telling me here I'm having a positive moment. So for the influence line, I'm drawing the positive up and the negative down. Okay, and this angle here is going to be 1 radian, and we're going to show you in the next class how we're actually going to use that. Right, so for now this is the influence line for the moment at C. So a couple of remarks that we need to be aware of. The influence line for the load functions considered above are all straight lines. So since they are straight lines, I only need the main or key ordinates, meaning I only need 2 points to draw a line. Okay, and then they are connected by straight lines from the required for such cases. And this is the technique that we used in computing the ordinates of the influence line. It may be more convenient to work from the force on the side of the section which is away from the moving load. You could, going to be maybe an added step, but again, this is what we found. But this is again only for simple beams. Now, if I have more than one reaction, it might be different, and I will show you that in the next example. Okay, so in this example here, I want you to find the influence line for the shear at B, right here, and the moment at D, right there. Okay, now, so you'll notice that we have 3 reactions, AY, CY, and EY. And this is statically determined because of the presence of the internal hinge at B. So usually for problems like that, I would first like to find the influence line for the reactions, namely AY, CY, and EY, and then tie everything else to those reactions. You will see how easy that is going to be down the road. So let me start off with finding the influence line for the reaction AY. Okay, again, so now I'm going to find, I have the load moving from A to B just before B. Okay, so if that happens, now I can find the value of AY by taking the moment at B is equal to 0. Here you notice that I have to take both parts because again I have three reactions, so it's not like a simple beam anymore. So if I take the moment about b equal to 0, then I'm going to have 10 AY minus this load, which is going to be 10 minus x, right? So if this is x, 10 minus 0, then AY is going to be 1 minus x over 10. If I do a summation of Fy equal to 0, then VB is going to be equal to minus x over 10. Okay. Now, and you can find that again here. Again, I'm assuming a positive shear sense. So if you do summation of Fy, then what's going to happen that AY minus 1 minus VB is equal to 0, which will come to the fact that VB is going to be equal minus x over 10. Okay, which means my VB actually should be upward. That's what this means, right? So with that being upward, then I'm going to have a negative shear value. Now, using this, I can find now the reaction CY and EY. So now I'm going to take the moment about C is equal to 0, with this being my positive direction. Then this minus x over 10, which is this one right here, times 10, minus 20 EI is equal to 0, which is telling me that EY is equal to minus x over 20. Make a summation of Fy equal to 0, then I can find the value for CY. So remember, these values of CY, EY, and AY, and VB are only valid for x between 0 and 10, because this is where the load is moving this way. Okay, so that's that part. So now what happens now when the load is moving in this direction? And here I just changed the origin of x and made that from this point right here to make things easier for me. So now if I look at AY now, there is no load, right? So if I take the moment about B is equal to 0, then AY is going to be equal to 0, which then means also that VB is equal to 0. So for this whole distance right here from x from 0 to 30, my reaction AY and my shear VB are equal to 0. Okay, so that would probably, now I have full information for VB, by the way. If he was asking me for VB, I probably could start right there. But he wants the moment in D as well. So I'm going to continue and find the reactions. So in this case now, again, this is going to be my positive moment. I'm going to take the summation of moment about E equal to 0. So then this will be, again, since my x is this way, so this is going to be minus x plus 20 times cy, and then cy is going to be x over 20. Take the summation of Fy equal to 0, then cy plus ey minus 1 is equal to 0, and this will give me the reaction for ey. Okay, so now I'm ready to plot the influence line for ay, cy, and ey. So for ay, again, since we have that divvied up between 0 and 10 and from 0 to 30, I got this 1 minus x over 10. So at x equal to 0, this is 1. This is 1 kilonewton. At point B, this value is going to be 3 times 10 over 20. So it's going to be 30 over 20 right here. For this one, it's going to be minus x over 20. So that's going to be minus 1/2 for EY at this point right here. Now here you've noticed I did nothing for AY because you said this value was 0. Okay, so now the influence line for CY, now here again this is going from 0 to 30, so this value is going to be 30 times 30 over 20, which is again 1/2, and this again was also 30, so you can see that this point right here is equal, right? Influence for EY, now this is the curve, which was 1 minus x over 20. Here you have to put in x for 30 and you will get minus x over 20. As you've noticed that for the influence lines, when this A here is equal to 1, then the influence line for CY is 0 and the influence line at EY is also 0. Now when this is equal to 1, then the influence line here is equal to 0, and this one is equal to 0 as well. For CY and AY, now with these two being both 0, this value is also 1 kilonewton. So now I have the influence line for AY, CY, and EY. I can plot VB directly, so VB was 1 minus x over 10, or it was simply AY minus 1, right? So if I only drew an AY, if I only drew AY, then I can do that, and we know that the influence line for VB was equal to 0. Okay. So now let's move on to the moment at D. So the moment at D, what I'm going to do here is, again, I'm going to assume that the load is moving. Oh, there is this internal hinge. Sorry about that. So the load is moving here, right? I'm going to look at this section. And for that, MD is just simply equal to 10 EI, right? 10 EY. Okay. So as you've noticed here, I didn't have to go off these hoops and find X and L. No, I'm just doing that with relation to my reaction. So the reason why I do that is, so let's say that he wanted to have more points on this beam. Let's say moment at C, moment at A, well, moment A is 0, so that doesn't matter. Moment at B, so I can always relate these to my reactions. And again, for some reason I'm forgetting the internal hinge here. So now with this MD, now here, for me, it's easier actually to look at this part, okay, so that I have it to one reaction, which is EY. Then by taking the moment at D is equal to 0, I'm going to have a minus 10 EY plus 1, 10 minus X plus MD. So MD now is 10 times EY minus 1 plus X. Okay, so again, I related that moment at D to my reaction at D. So I'm going to do the drawing. I'm going to first of all draw you the value of the influence line for EY. Okay, so now I'm going to go with X equal from 0 to 30, which was from here, right? And for that, MD is equal to 10 EY. So if I multiply 10 times 0.5, you're going to get minus 5, right? And plus 5. See how easy that is? All I did was just, now here at this point, I just could literally connect this because I know that the influence line at D is equal to 0 regardless. So I don't need actually to do this if I wanted to, but I just did it anyways. So I'm going to get this straight line. So if this was the only thing that happened, and you know this is a reaction, you actually don't need to use the step. You could do this, stop here, and then just go straight line to 0. And that's your influence line for the moment at D. I guess for you, if you want to have some exercises, I probably would ask you to find maybe the shear at, let me call this point G, and let's say this is at 5 meters from here. Okay, so maybe try and find the shear at G and the moment at G, just as an exercise for you guys, just to make sure you understand what's going on. Here I'm going to do something a little bit different. I want you to find the influence line for the shear at B and the moment at B. So the moment at B I have no problem with, but the shear at B. Okay. So here you have to understand that this is the shear at B, not the reaction at B. So the reaction at B is completely different than the shear at B. And to show you that, so here I'm actually taking this beam into 3 parts. So the first part is going to just before the reaction, which we usually call VB left, and I'm having a moment. And then here is at the support BY, where I'm having the shear. Again, I'm assuming here positive shear, okay? All right, so this is here my positive shear, and also I'm assuming here positive shear here as well. So BY is going to be equal to VB left plus VB right, okay? And then this part is where I'm going to have VB right and the moment at B. So this load is going to move up to the support. So again, I'm using 2 parts. So now if I take the right part, and again, X is between 0 and 4, then if you look at this part, there is no load, there is no force, then the moment at B is equal to 0, and the shear and VB right is equal to 0. So since VB right is equal to 0, right, I can take the summation of Fy equal to 0, right? and use this support part right here and say VB left plus BY is equal to 0, then this is telling me that VB left is equal to minus BY. So I did not even have to go to that part. I could. I mean, it's going to be just simply AY minus 1 minus VB, and then you can have the relation between VB left and BY, or you could do it like this. Okay, so this is only for the support. Again, this is valid only from here to here. This is where the load is moving. Now, when the load is in this section here, okay, here I'm going to take the left part. Why? Because I'm going to do summation of Fy, right? And then VB left, which is this one, plus AY is equal to 0, right? Then VB left is going to be equal to AY. So as the load is moving here, my VB left is going to be AY. Here, if you notice, VB left has actually values as long as the load is moving along the beam, while VB right was 0 for some instances. Taking the moment at B is equal to 0, then 4AY minus MB is equal to 0, then MB is equal to 4AY. Take the right part now to find VB right. I'm just going to say summation of Fy is equal to 0, then VB right is going to be equal to 1. Okay, you could have used it as support if you wanted to, but then you have to do some manipulation between BY and VB left and add that to AY. But this is a clear-cut summation of Fy equal to 0 and VB right is going to be equal to 1. So again, I'm drawing the AY and BY, and I leave that up to you to find the influence lines for AY and BY. If you wait till next class, you will see how easily you can find this actually without doing any calculations whatsoever. But for now, this is what we have. So now we know that VB right here is equal to 0, right? And we know that VB left is equal to minus BY. So I'm just multiplying this by minus 1. So this is the value for that. Now, when x is between 4 and 6, we know that VB right is equal to 1. On the other hand, VB left is equal to this. Okay. Any questions? Feel free to. Well, not any questions. I left out the part where we draw the influence line for the moment. So before I leave the slide, as you can see, the influence line for the shear at B is different. Here you have to deal with the right portion of that shear and the left portion of that shear. Okay, so these two figures, and let me use a different color like that. So this influence line here, both of these, okay, represents the influence line for the shear at B. Okay, you need two. You need VB right and you need VB left because it is at the support. Okay, now going to the influence line of the moment at B, we know that this was 0, so there is no need. And then this becomes 4AY. This is minus 1.5. 4 times minus 1.5 is giving me minus 2, and that's the influence line for the moment at B. You guys enjoy. Have a nice day and stay